Current computers don't operate like most machines, from steam engines to cars to rockets, or in fact any persistent system from whirlpools to living things. There is no feedback loop in terms of operation where energy is recycled. A computer may have iterative loops in terms of logic, but in terms of current flows, energy comes in one end and out the other as heat, flipping switches along the way. This brute force flushing of energy through a system is wildly inefficient. Until now, this inefficiency was masked via miniaturization. However, as we'll show, not only have we reached the end of the road with this approach, but it comes at a time when we're seeing a step change in computational requirements driven by AI. Since the advent of the transistor, chips were able to increase in performance through miniaturization because the power density remained constant since voltage and current scaled down proportionally with the size. This reached a threshold in the mid-2000s where this no longer applied, and as a result, continued performance increase via Moore's law could only be achieved with clever tricks and increased complexity. Heat generated with computer chips has become a bigger and bigger problem, to the point where Moore's law no longer necessarily applies at all. With ever-increasing demands for more and more computation accelerated by AI, not only is heat a problem for continued performance increase, but the cost of the power to run the chips and cooling systems to deal with the heat creates a problem from an operational cost and efficiency basis. Today, a third of Ireland's electricity is used to power data centers alone. Clearly, something fundamental needs to change with the way chips operate, and while people have been distracted by the seduction of unproven or exotic new approaches to computation, these are not tackling the current problem of unsustainable power and heat requirements using technology on the immediate horizon. The one-chip architecture that offers a potential solution to these problems would have been out of reach were it not for the structural changes to the industry that AI has triggered. AI delivers both the attainable market and the go-to-market opportunity, as it creates a massive demand for both edge and server-based low-power computation, and that these are addressable via a much simpler suite of operations, largely consisting of matrix multiplication. The architecture that offers a solution is reversible computing. Tackling the problem of heat loss through energy recycling forces us to create circuits that allow currents to flow both forwards and backwards, through logic gates that are themselves reversible and via resonator devices that allow clock cycles to alternate forwards and backwards, like a pendulum. Reversible computing architectures such as this can vastly reduce electrical energy use and subsequent heat, where an engine with no heat loss is said to be adiabatic. Adiabatic chips reduce wear and tear on transistors via more gentle and smooth processes, and therefore increase chip lifespan, as well as requiring less power and less cooling. Running chips more carefully for ultra-low energy consumption means running more slowly, but there are many immediate go-to-market applications for ultra-low energy chips, regardless of cutting-edge performance, particularly for so-called edge devices where things like AI models are run locally rather than sent to a server. As the performance of reversible chips evolves, the speed disadvantage is offset by the ability to pack more densely without heat issues, even opening up the possibility to layer in 3 dimensions, much as is currently being done with memory chips. Overall, reversible computation allows for higher performance per unit volume with lower energy use for high-performance server applications. An adiabatic chip requires reversible compute, as recycling, by definition, means circuits working in a cycle, both forwards and in reverse. But this solves a problem which is further off but completely unavoidable for digital computation itself, that has nothing to do with the analog world of electrical circuitry. This problem was first identified in the 1960s by Rolf Landauer, and states that deleting a bit of information necessarily releases a certain amount of heat. Since nearly all of the logic gates in non-reversible computing have 2 wires representing bits of information as inputs and 1 as an output, there is a bit deleted, and all modern computation necessarily produces a certain amount of heat. This in turn means that there is a minimum amount of energy that has to be input, as you can't create heat energy out of nothing. So there is a brick wall unless the inputs and outputs are balanced to make them work both ways and no information is deleted. And so reversible compute future-proofs the fundamental architecture of computation to avoid an unavoidable brick wall for the way all computers currently work, and which can only be solved by both two-way energy and information recycling. If Adiabatic solves the current electrical problem that has complex workarounds that will eventually dry up, and Adiabatic in turn requires reversibility, reversibility solves the future information theory one that has no possible workaround without reversible computation. Energy and information recycling are doable, but it requires multiple steps of hard engineering and iterative learning based on a completely different mindset from incumbents. Success unlocks a multi-trillion-dollar opportunity of societal importance to make abundant computation possible within a sustainable energy budget.